Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be starting our conversation about atomic theory. So really what we're going to be doing this chapter is we're going to be really looking into what makes an atom and how do they work. So we're going to go ahead and start by trying to take a historic view of figuring out how atoms were discovered and what are the key properties that define them. Then we're going to dive into the exact atomic structure of an atom and try and figure out how atoms of different elements differ. So what defines carbon versus nitrogen versus oxygen? And this will bring us into a good introduction of the periodic table, what it is and how we can use it. And looking at isotopes, so these are going to be the same atoms of the same type, but have slightly different properties. And then ionic species, where now we're looking at, again, two atoms of the same element, but they have different numbers of electrons, which gives them a different charge. And then we're going to try and scale up these atomic level properties into macroscopic or visual properties by bringing up the mole, and then looking at how atoms can come together to make basic molecules. So let's go ahead and dive in by taking a historic view. So most conversations of atomic theory start, as most classes do, with Western philosophy. Whether it's fair or not, most of the time we tend to look back at the Greeks. So one of the big things is Greek philosophers had a very popular conversation of looking around the world and saying, what made the world? And so they tried to divide the world into base elements. And so this is where you get the classic philosophies of fire, water, earth, and air. But you also have some people introducing wood and metal as base elements. However, someone took a different tack, and this was Democritus. And he proposed that all matter could be cut into individual bits, and you can keep cutting it till you get to one particle, what he called the atomos, which literally, by its definition, can't be cut any further. So this is the indivisible part of matter. And if you understood the atom or the atomos, you could then use that to build up the rest of the world. So the classic analogy here is by looking at grains of sand. So you can go ahead and you can take a big desert and you can divide it into smaller and smaller sections. But at the end, you'll eventually reach individual grains of sand with space in between. However, it turns out the early Greek philosophers didn't like the idea of a non-continuous world where there's little spaces in between particles. So Democritus kind of got put on the back shelf until about the 17th century, where you had the dawn of Robert Boyle. So he introduced the concepts of elements, compounds, and mixtures that we talked about last chapter. But it is worth noting, at this point, we're still more alchemy than chemistry, because he still spent most of his time trying to turn lead into gold. So chemistry wasn't quite there yet. However, several early scientists tried to build on Boyle's work, and these are most famously Black, Priestley, Scheele, and Cavendish, who were looking at air and discovered that air was actually a mixture of different elements. And they were able to start to form a composition of these compounds and elements. So they were starting to say, wait a minute, we can apply this atomic theory into gases. And this really laid the groundwork for one of my favorite scientists, Antoine Lavoisier, who lived in France in the middle of the 18th century. So one of the big things that distinguished Lavoisier from almost everyone else is that he weighed the mass of a substance before and after a reaction, because he actually started his scientific career as a tax collector, and most famously, the tax collector of Paris. And he thought it was so weird that they brought so much food into Paris, but shipped out so little poop. And he thought that the mass coming into the city had to equal the mass leaving the city. And so he wanted to figure out where that missing mass came from. So he decided to look at simpler reactions and actually human respiration. And he was the first to discover that a lot of mass is lost as air. So for example, you can take mercury oxide, and if you heat it, you get mercury and oxygen. He was also the first person to realize that the sugar and other food you take in your body most of the mass actually leaves as CO2 and water vapor. So you actually lose most of your weight through breathing. And this important idea of the conservation of matter, the mass that comes into a system has to equal the mass coming out. And if you're missing mass, you're probably not looking hard enough. And so again, he came up with with elaborate environments so we could measure the amount of gas being leaving a system. However, it doesn't pay to be the tax collector of Paris during the 1780s and 90s. So he was also famously executed on the guillotine during the French Revolution, which is the reason why his wife, Marie Lavoisier, was so important, because she was the one who recorded all of his notes and published all of his findings. And it's through Marie that the modern world knows about the law of conservation of mass, really making her one of the important figures in science, because it doesn't matter what scientific discoveries you make, you have to make sure you communicate them appropriately. So building on this, we had John Dalton. So he ended up proposing that a compound is always made of the same elements. And not just the same elements, the exact same ratio of elements. And this is often rephrased by saying that a certain species or compound has to have a constant percent composition. This is one of the things that makes a compound different from a mixture, is that it always occurs in the same ratio. And so this was most famously illustrated for carbon dioxide. So it always has a mass ratio of 2.66 grams of oxygen per every 1 gram of carbon. No matter what the total mass of the sample is, the ratio is always the same. That means that if you end up identifying a mysterious material with this ratio of oxygen to carbon, this likely means you found carbon dioxide. And then he took this one step further and came up with the law of multiple proportions. And what this said is that if I have a different molecule that's made of the same elements, so carbon and oxygen, it should contain a different ratio of these elements. So for example, carbon monoxide, it's got a ratio of 1 carbon atom and 1 oxygen atom. It's colorless, odorless. You can go ahead and burn it with extra oxygen. It produces a blue flame, and it binds to hemoglobin and causes death. Carbon dioxide, however, has a ratio of 1 carbon to 2 oxygen atoms, still colorless and odorless, and still a gas, but it doesn't actually burn. And most importantly, it doesn't bind to hemoglobin. So it isn't, well, toxic, it isn't nearly as toxic as carbon monoxide. And so Dalton, in addition to coming up with these law of proportions and multiple proportions, he put together the first definitive atomic theory, where he said that atoms should go ahead and follow a set of 4 key rules. First, matter is made up of atoms. So if you have any form of matter, it's going to be made up of atoms, which are just, again, these tiny particles. Atoms of a given element are all going to be the same, but atoms of different elements are going to have different properties. Now, if you end up making a compound of a given set of elements, they should combine in certain whole number ratios of, say, 1 carbon atom to 2 oxygen atoms. And during a chemical reaction, these atoms are only rearranged. You do not change or destroy atoms. And it's worth noting that over about 200 years, these rules in general have held up pretty well. It turns out that there's only several small modifications. It turns out that atoms themselves are made of tinier particles, which we'll talk about a little bit more next time. It also turns out there can be subtle differences in between atoms of a given element, which we'll talk about later with isotopes. And that we also have nuclear reactions where you can go ahead and actually destroy or generate new atoms. But this gives us a very solid starting point to really build up the ideas of chemistry. So next time, we're going to go ahead and dive in a little bit more into the composition of atoms. Until then, take care.